the end of the term. Since this is the last content lecture, let me take a minute to first celebrate. So I think the TAs this semester have been absolutely off the charts good. So all three of them have been incredibly good. Yes, Sava, actually. The department gives out a few awards, and Sava just got a teaching award that he's going to be recognized with next week. We just found out. So congratulations to Sava. But to all three, I really think everybody has done just like an off-the-charts good job. I normally am like so active on Piazza, but I cannot get there faster than Sava. So I have been almost unable to do it. Okay, so yeah, very well deserved. I've been promising that we'd talk about a little bit more about what's happening with all the learning stuff, and I want to do that today, right? And I want to do it in the context of what we've already learned, and I hope when we're all done, we feel like it's, consistent with what we've already learned and not just something totally different and new. So last week we did a little bit about output feedback, right? And in particular, we went from treating the plant as, having a magical state output port to now we're going to sort of admit that the plant is more complicated than that. It has an internal state. Maybe it's got disturbances and noise coming in, but it's got some sensors coming out, which may be a very noisy version of what the true state is, a subset of what the true state is, occluded partial views of what the full state is. Okay, and there's a whole additional challenge of trying to make good control decisions only using the sensors available to you. And one view of that was that we're going to use the sensors to try to, and the actions, to try to do an estimate of the state. But the more holistic view of that really was we're going from policies that were of the form, taking X in and putting U out, which we know the optimal policies can be just a static function of X, to a more dynamic view of what a policy needs to be. Right, where it has its own state, we can call it X of the controller. It's taking observations in, and it's making streams of actions out. Okay. Now, considering its importance, I gave you some of the basic tools that we have for this sort of output feedback case. LQG being the natural extension for linear optimal control with Gaussian noise. There are versions that I alluded to of doing like sums of squares on alternations or other things. There are tools that will penetrate a little bit into this world, but not enough in my opinion. Okay, and in particular these days, the sensors that maybe we most care about in a lot of applications tend to be cameras. So I feel at the end of the term, one thing that I wish I had a better solid answer for, but we haven't really given you the recipe for yet, is how do you do really good feedback control from RGB? Okay. Certainly there's pipelines where you have, let's say, depth cameras, and you can write state estimators that try to reconstruct the state, maybe with some geometry computation. You can do pose estimation. I go into that a lot more in the manipulation class about all those kind of tools. Those are strong pipelines for some applications, okay? But somehow, the idea of using color-valued cameras, RGB cameras, we haven't given you great tools for that. And I would say, when I was a young roboticist a long time ago, and I started talking to the control theorists more and more, it really did just it changed my worldview to be able to talk to people who were so immersed in control, and basically I felt like they could think rigorously about almost any problem. Like I have some very complicated robots that I care about in my life, right? But they could just penetrate right to the heart of what was the essence of these control problems, and almost always had a good answer, or at least a path forward. Like, okay, here's a problem we can't quite solve, but there's a path forward. Until you say cameras. And then the control theorists mostly leave the room, right? It's like, it's not a bad problem, it's just not our problem. And it's hard to think about with the tools of control. And for good reason, right? It's not that, I mean, there are a few control theorists that do vision, but they're, you can count them on one hand, kind of. And it's for a good reason, right? So let's just appreciate what's happening here. So, in Drake, for instance, we might have a diagram that's a multi-body plant and a scene graph, okay, hiding under there. Those things, that's already a little bit complicated. And then the scene graph is what tells us how to make our RGB sensor model, okay? And this puts out an image, okay? And this was the one that takes in the actions. So the system that we're trying to control in a RGB-based feedback sort of space is really kind of that system, right? And there's things that we know and love about the manipulator equations, right? All that stuff, right? There's structure there. There's, smoothness there. Knowing something about a queue over here tells you something about neighboring queues, right? There's lots of structure there. But, this thing here is a full-on renderer. This is like a game engine quality renderer, right? It's taking the geometry, it's projecting, it's doing projective geometry and the like. It's casting shadows, it's doing a lot of, messy tricks to make beautiful images come out the other side. In some cases, it's doing ray tracing, but actually a lot of them are not, right? Okay, so, and you might have heard of, let's say, differentiable renderers, right? This is a thing that became popular a couple of years ago. I remember when it happened. But even though I was very excited about that when the idea was new, I'm not sure, and I hope I'm not offending anybody here, but I'm not sure how far that goes, because you can take and you can pass gradients through your renderer. You can even change some of the operators to be a little bit more deterministic and a little more smooth or something like this. But still, sort of fundamentally, the problem with projective geometry is that, if I've got a box here and it's in pixel 32, then pixel 33 may or may not have anything to do with the pixel in 32. Does that make sense? Like there's rough discontinuities, edges. You rasterize, you do things, and you smooth those out a little bit, but it doesn't have the kind of global structure that we have over here. There's kind of, gradients, if they're given to you, are very local. And basically, although it is immensely important because of the power of our cameras and everything, RGB is just like a terrible space to do control. Pixel space, I think, is just, if you've got a control system and you like in the middle goes through pixel space, then you're just not happy, right? It's a very bad space to represent things in. On the other side, the things that started working, and we'll talk more about today, I'll put a deep network or something like this to go back from here down into some other representation. This gets complicated fast too, okay? But maybe there's more hope if we can make this our black box and go into pixel space and then come back out into some slightly more manageable representation, right? This could be, explicitly you're trying to do reconstruction of the geometry. It could be tracking key points. It could be trying other things. But in most cases, there seems to be, you can ask for these representations to have certain properties, but they can be better than just operating directly in RGB. Okay, so starting in 2012, we had AlexNet and we had ImageNet. That was kind of when the deep learning revolution started. It took till about, 2016, I think, was when we started saying, what would happen if we took one of these things that was trained initially for image recognition and put it as the front end of our controller, right? And what would that look like? What would the pipeline be where I start off going out of pixel space into some better representation with the new representations from deep learning? And that was the beginning of the sort of visual motor control, right? And the paper I attribute it to is this 2016 paper by Sergey et al. Okay, they started taking a pre-trained ResNet, a ResNet that was trained on ImageNet, for instance, okay, and said, what if we took that and we shoved our image there, maybe even a history of images in here, okay, and we got to some intermediate representation. The robot sensors, our joint angles and things like this, we don't have to send that through the full network. We'll send that through a much smaller policy network. A lot of times you'll see nowadays people put snowflakes saying this part's frozen, right? And this part could be trained. Sometimes you'll have to train all the way through to be successful, okay? But the essential thing about this architecture is that there's some intermediate representation Z here, a latent state Z, which you can think of as something like the dynamic state in your controller, if you like. We'll make in some cases it'll actually be a dynamic state, but it's some intermediate representation in the state, okay? And this, an old idea, but it started working extremely well with the new tools from deep learning. Okay, so this was the first sort of recent, in the age of deep learning version of this idea, deep visual motor policies. I'll fast forward a little bit to some of these tasks. And in 2016, we started seeing robots doing things that looked complicated, right? They were hanging hangers on a rack. They were doing, they're not complicated in a dynamics and control sense, right? They're not at the edge of stability. They're not at the joint limits or the torque limits, but they're hard to model potentially. There's a different axis of stability. It'd be hard to generate a model-based controller that would do this directly from cameras. Okay? It's not a new idea, I should say, right? This is like the way that they trained that control, those visual motor policies, was with imitation learning. So and just to be clear, there's kind of two, I'd say, mainstream approaches to imitation learning. One of them would be behavior cloning, which is the one we'll talk about mostly today. Cool kids call it BC. The other one would be inverse reinforcement learning, or inverse optimal control if you're a negative person. You use cost functions instead of rewards. Yeah. Okay, so behavior cloning is making control into supervised learning. Okay, so I'm gonna take in now. If someone is a human giving me demonstrations that look like a policy, I have a sequence of observations in, I have a sequence of actions out that come up from a human demonstration, and I want to train. So I have a human demonstrations giving me this. And I'll train my big deep net, my visual motor policy. Okay, this becomes now a supervised learning problem. Behavior cloning is the supervised learning. In its full richness, it's a sequence learning problem. You have a sequences of Y coming in. You have a sequences of U's coming out. So it's really a sequence learning problem, okay? But it's trained with very simple objectives, like I'm going to minimize the expected value of U minus my predicted U. Squared, let's say. Very simple reconstruction losses. Just try to match the demonstrations. Okay. And this isn't unique to robots, really, right? So AlphaGo does, the first thing AlphaGo did was they took human demonstrations of people playing Go and tried to learn a policy from human experts, right? It went on to do more than that. It went on to do RL and self-play. That's the most famous part. But you have to remember, it started actually with, it got off the ground by just mimicking humans, right? For me, so that, I think Sergey and Chelsea and everybody did that in 2016. By 2017, I was trying to play with it in our lab. This is Pete and Lucas led this project on doing visual motor policies. We had a particular type of representation that we were proud of, using dense descriptors to do to represent that Z vector, okay? But really the point here is that this happened in our lab, and this was the first time I got to experience it. Like I got to see from the training, you know, through to the performance. I got to stick my hand in there, shake it around in front of the camera, push the plate around, and this just changed my worldview. Like it's like these things are can be very, very robust. They can also be hilariously fragile in certain ways, but it really, well, first off, I think using cameras as a sensor at high rate is just super, super valuable, right? And the fact that I had kind of been working around that, I didn't fully realize how much I was skipping. And it's not just the depth information. I remember the days when I asked these guys, I said, okay, let me just, as a test, you know, if I were to say you can only have depth or you can only have RGB, which one would you take? And they said RGB. At this point, I would take RGB because there's so much information in the task that describes the task. It comes from the RGB values and not just the geometry of the task. It's actually the context of the task. And of course, RGB gives us, I mean, it really, you could come in there, and we had another one where it would put your shoe on a rack, and we would, like, basically anybody would come in and set up, we would ask everybody to take their shoes off, and it would just take the shoe and put it on the rack. It was like super fun, super robust. Really changed my mindset. That was trained, okay, so I mean, did all kinds of these different tasks, okay. That was trained with a very simple pipeline, right? So Pete made a mouse-based teleop interface, right? He set up the shoe 50 times, right? 100 times, 200 times, maybe, if it was important for the paper, right? And you do the task enough times with enough different variability, and you train your policy with supervised learning, then we started to get these amazing outputs. Okay, the policy for the shoe wouldn't work for the box. You know, you train one per task. Okay, but that started to really, really work. And teleop is getting better and better. This one is just the other day from the Optimus, the new Optimus, Tesla Optimus. But you just see there's like fleets of people in VR teleoping dexterous humanoids, right? It's the future of work. No, it's not the future of work. But it's teleop has gotten better than Pete's mouse and keyboard interface, right? There's a lot of, and actually, the Vision Pro and all these things, that the teleop interfaces are fantastic, and there's richer and richer haptic teleop interfaces. So you can do a lot of things through a teleop. The mental model that we had at the time, and I would say I still have in the single task imitation learning, is roughly that the networks are, we distinguish in deep learning between generalization and extrapolation, interpolation versus extrapolation. Okay, so if you give a bunch of training data, and we found a clever way for one of the tasks to project this down onto sort of a two-dimensional image, and we said basically each rollout was kind of one of these blue dots. Okay, and then we started asking how well would it generalize, right, to new initial conditions and the like. And roughly speaking, if your new initial condition is in the convex hull of the things that the demonstration that you demonstrated, then you have a fairly good chance of it being doing a good rollout. Okay, but once you go outside of the things that's seen from the demonstrations, all bets are off. Sometimes it works, sometimes even in surprising ways it works, but mostly you're getting lucky if it worked like that. Okay, so that we got to sort of the field got to the next round of sort of doing behavior cloning demonstrations. And you got to you could really put on a good manipulation demo with these sort of behavior cloning pipelines. Andy is one of my favorite people. He gave a talk here a while ago, 2022, and he had this beautiful slide that I think it really did capture it nicely. So not so secret recipe to making a rock star behavior cloning demo on real robots. So first off, you have to collect your own expert data. Don't let just anybody give the teleop demonstrations. The person doing the teleop has to know a little bit about the limitations of the teleop system, of the robot, of the imitation learning pipeline. Okay, there are little things like no action data. If the robot's ever just frozen, then that's always going to be a solution, and you'll never leave it. All right, and then trying to collect enough data to cover all of the things that might happen in your demo, right? And train and test the same day, because you've got cameras going on. So if the light's different or whatever, so you could be potentially fragile in that way. Okay, so that was 2 years ago, right? So what's happened in 2 years? It's crazy what's happened in 2 years, right? So self-supervised learning was already happening a bit, but it's happened in a big way now, right? And the way it's most visibly happened is in large language models, right? So whenever you've seen these text completion prompts in your Gmail or whatever, you're training some big model, right? The key idea is that it's predicting what it's giving you a guess. You're giving it now the label, and you're giving it supervised learning training data, right? And you could say GPT, the first step of GPT is exactly a behavior cloning objective, with exactly a sequence model, right, that's taken a history of recent tokens coming in and has to predict the next token. Right? So GPT, I think, is trained on the entire internet, so that's got a big data set, but it is just doing next token prediction, which is behavior cloning. And then, of course, they do RLHF and other things to try to make it more likable, but the underlying intelligence maybe started with behavior cloning. So that's actually, it's worth making that point. Okay, so one thing that people often say, which I think is a little wrong, or you have to be careful with it, often say that it's one of the things that's limiting about behavior cloning is that you can never do better than your demonstrators. Right? That's a very easy thing to say. But GPT does some things that I don't think any human could do, all the things GPT can do, right? So there's something that can happen with generalization, and there's even theorems in the early BC papers saying that it is possible for the learned system to outperform the original demonstrators. Okay, so I don't think it's going to invent something incredibly new. That would be too optimistic, but I don't think it's fundamentally limited by, especially when you get into the big scale things, by the quality of individual human demonstrators. Okay, so then move on a little bit. We got generative AI going for images, right? And how does that work, right? People put a lot of captured images on the web, right? And then now, it was funny, I was looking for sort of a history of this, and I remembered I gave a talk at the robotics competition kickoff, like the first robotics, back in 2022, you know, when they were unveiling the board, whatever, I gave a little talk, and I was trying to tell them about generative AI, and that was DALL-E 2 at the time. So I said a painting of a professor giving a talk at a robotics competition kickoff, and they got that out, right, which is pretty good, right, at the time. And then a year later, I was giving a talk at this is my kid's high school, so I was embarrassing her. I'm like a handsome MIT professor, but I mean, pretty incredible what happened in a year. Like just actually by the calendar, a year. Okay, so pretty, and they all have hair. Okay, so how does that work? Because we're going to connect this back to control, right? So. Of course, an image is just a list of numbers, of pixels. So you could imagine taking that next token prediction analogy and just sort of doing next token prediction in terms of like next pixel prediction. And that's not so different maybe from what a VIT is doing, but actually that's not what is the main core idea that powered DALL-E and stable diffusion, right? It's this diffusion idea, okay? How many people feel like they've heard about, feel like they kind of know diffusion? Yeah? So it's easy to talk about. It's actually easy to implement. Devil's in the details. But the basic idea is how do you make self-supervised, you know, you don't have someone typing in email and just auto-completing their sentences, right? You've got to do something else. You've got a bunch of images online. What do? You take all those images and you make your own data by adding random noise into the images. Okay, you're making new images. But by adding noise this way, you're making pairs of you know, clean image, noisy image. And then what you do is you use that to train the opposite, the denoising process. Yeah? System identification? Okay, there's probably some connections there, yeah? Yeah. Using noise to do exploration sort of things, excite the dynamics. I mean, I think the idea is, you know, drawn from physics, right? But, and it's just turned into some very simple, you know, it's the original derivations were deep in sort of talking about score functions, log probability distributions and the like. The algorithm to implement it is actually super, super simple. Okay, so I can write it down in like 3 lines here. Okay, so in a nutshell, step 1 is you do some sampling. Typically X, even though I call it state, X is the thing you're diffusing always in diffusion. So you draw some X from your image data set, let's say. Okay, you also have to pick a noise level. In some range of possible noise levels. Okay, and then you pick a noise direction that's in okay. Then you add that noise to your image. So let's just call it X sigma is just my original image plus the noise, which is just parameterized as a combination of the noise level and the direction. And then you take one step of gradient descent. To minimize the expected value of this by doing it lots of times. So it's, even though we show this picture all the time, the thing that people actually do in practice is they take this cat, they pick a random noise level and they jump all the way to whatever that noise level is, and they learn the mapping that jumps all the way back. Okay, so it's not actually, even though you learn it at many different levels, but you just do them all the way back. You learn the mapping all the way back. And this sigma, or this epsilon here is called the denoiser. And it's a neural network parameterized by theta. And you have to tell the denoiser what the noise level is, too. That's why we separate out and call the noise level and the noise direction separately. So given the noise level, given a noisy image, predict what the direction of the noise was. It gets me back. That's it. Okay? And that gave us there's some other bells and whistles about trying to do guidance to get really beautiful images out, but you train that on the internet's wealth of image data, and you start getting amazing images out. Okay? I'd actually recommend, Shenyang's got a fantastic little tutorial now about this. And this is one of his examples that I was playing with a bunch, and I like a lot. So imagine you just did in 2D. Your data was just drawn from a spiral. Okay? So these are the samples. They were drawn from a clear distribution that was a spiral function. Okay? What does denoising diffusion do on this? Okay? It learns a function that basically takes a random sample and pushes it back towards the manifold. There's an interpretation of that the denoiser is roughly learning the distance to the data, basically. The pushing you back on the manifold. It's a little more subtle than that. At high noise levels, it's moving you back sort of towards the mean. And somehow some combination of this makes incredibly efficient inference and converges on the distribution of your original data. Yeah.
I'm not familiar with the term manifold. You just mean the original image?
So each point here would be comparable to an image. This is a cat, this is another cat, this is another cat, okay? And I'm projecting that high dimensional space down into a two-dimensional space. I'm thinking about the manifold as somehow the manifold hypothesis as like the images that you get on Flickr or in the world somehow live on some lower dimensional space. Not all pixel values will ever appear on Flickr. Right? There's somehow some manifold of cats, okay? And so this one we intentionally designed the manifold to be drawing samples from that spiral. So what we'd like is that when we sample from that, we'd get more samples that look like they were drawn from that spiral, if it captured the essence of the problem. And it does that beautifully. And it does that by learning this sort of projection back to the data manifold in the simple case. It gets more rich when it's a less of a deterministic manifold, but that's, I think, a pretty good mental model of what's happening. Okay. So take diffusion and stick that. That worked well for images. Let's pineapple pen that back into, there's a kind of joke in the lab about doing pineapple pen research. If you've seen the video, you know what I mean. If you don't, that was just a weird thing to say. Okay, but this is two very natural ideas, right? We know how to do behavior cloning. We know that generative AI is doing incredible things with high-dimensional outputs. What could you do if you put those together, right? And that's what gave us these things that I've shown you a few times at the beginning of the lecture, right? Now we have behavior cloning that can just do insanely dexterous things with a very small number of demonstrations, right? So I really, like almost every dexterous manipulation task that I ever had on my bucket list has now been done. Time to retire. So this is the way to think about that in terms of diffusion. So take a simple task, pushing a T around. You'll see some T pushing next week too, I think. One of the project videos, okay? So that's human demonstrations, right? Just pushing that down. And then what does diffusion look like in this? Well, instead of diffusing the image of a T or something like this, it's going to diffuse a trajectory of future actions. Okay? So it starts with a random trajectory. That's why it started off with just pixels all over the place. And then it denoises down into a coherent trajectory, which is an end effector trajectory, which is drawn from the same distribution as the sample data. Okay, and that turns out to be a surprisingly effective way to do behavior cloning. Okay, so let me just write that carefully. So we're going to, in the diffusion policy, you diffuse an action trajectory. Okay, so you pick some horizon, just like in model predictive control. We're going to predict some, we're going to make decisions for the next m time steps, okay, and then we're going to execute a few of them, and then we're going to plan again. So think of it a lot like a model predictive control setup, okay. And then I think the cleverness that made this stuff work so well, and Chung is absolutely amazing, and the execution on this was fantastic. There was a bunch of small decisions that made this really super effective, right? So the denoiser, where you think of that as being, normally I said it was I'm going to denoise X based on sigma, okay? So I'm going to take my noisy thing, X sigma, and then M sigma, and try to denoise that. We're going to additionally condition this on the, let's say, history of observations. Recent history of observations. It tends to be a short history, actually, in the demos you see. So think of that as being the neural network that is doing the denoising just has additional inputs for the original images. And those go through the ResNet, ImageNet pre-trained backbone initially. Increasingly, they go through big transformers to get there, okay? But fundamentally, it's just a combination of the visual motor pipeline with the diffusion pipeline. Okay, I mean, this is the sort of from the paper, the architecture slide, but it's going from histories of observations to histories to future predictions of action sequences, and then you have the denoising diffusion layer at the end. So you do it encoding into an observation, and then you have there's a particular UNet sort of form of the output layer that people tend to use since the original diffusion papers, but those details I think don't matter as much. These are big networks, but not GPT big. This are not language model big. You know, so a language model is billions, 70 billion parameters are the small large language models, right? Let's say this is 100 million, so teeny by those standards, okay, but big enough that it takes a couple GPU days to train, which you do in parallel in a couple hours, of course, but it takes hours to train them. Yes?
The training data is all expert demonstration, so somebody just putting the TE back?
Yep.
How many times?
Yep, typically we say 50 to 100. If we're going to try to make it good, we'll go to 200 or something like this. Yeah. Yeah. Yes?
What space do your actions set positions to? Does this work for other spaces as well?
We've seen it in a lot of different spaces. At TRI, it's mostly end effector commands, and then we send it through a low-level controller that's giving us our safety case, if you will. So it's differential IK or operation space control, just so the robot doesn't slam into the table or something like this. We've done it in joint space too. For like the Puño project was all in joint space. We've seen other people do it in. I don't know if I've seen people do it in Torque. I'm not sure if I would know, but we normally send it through a low-level controller. So I want you to think about that as a dynamic output feedback, right? So this is a dynamic control policy, right? And this is now taking a history of the inputs in as a function, okay, but that's just a sequence model that's doing a dynamic output feedback. That's the autoregressive form, just like an LLM is a dynamical system, okay? But this is just another dynamic parameterization of a dynamic policy. It happens to have diffusion in the output in order to predict the future trajectories. I would say diffusion policies are one of like 3 architectures that people are using a lot for the behavior cloning demos you see. There's another one from the Aloha. I'll show some Aloha videos later that does a CVAE sort of representation. So they're using transformers, a BERT-style sort of transformer. I won't go into that in some detail, but there's other things that can definitely work. But let me make the sort of the key point I think that's good about the diffusion representations is that they can handle complex distributions of continuous action spaces. So I think there's some class of models, like if you've seen Google's RTX, RT1, RT2 models, those are discretizing the action space. And then you can predict discretized actions, and that's okay for some things. And I'll try to make an argument for why that's good. In diffusion policy, we're not discretizing the action space, but we're still learning distributions. Did you have a question? Yeah.
I'm just trying to understand the intuition here. So when we are sort of modeling regular feedback problem, right? So for example, here, like we have bounds on the actuators and the control input. This is not like this is a human demonstrating putting the key back.
Yep.
Then the policy, when you're writing that out as a diffusion model, that's also not taking any of those constraints into account. So how does that?
Good. So how would we handle like torque limits or joint limit constraints or something like that? The simple answer for you is that we make the we subject the human to those limits also. So the human is going through a teleop interface and has the sort of the same action space, including input limits and constraints that the robot does. So the demonstrations should be faithful to those constraints. There's a second answer, and I think the work in the diffusion repo that I recommended, it actually gives a deterministic interpretation of the denoising diffusion as going back to the manifold. If you like that definition, then that gives, and there's a few people that have thought about different ways to do this, you can imagine denoising subject to some constraints. You're basically doing now projected gradient descent back to a manifold. If you wanted to post hoc add new constraints to your rollouts, you could steer your denoiser subject to those constraints to find satisfying solutions. We're not doing that in these demos, but I think there's a path forward to doing that kind of thing. Yeah?
Why would you ever discretize your actions instead of modeling the system stochastic, the premise of distribution?
That's the point I wanted to make. So let me make that first, and I'll come back. Let me make that in a few minutes, because otherwise I'll get completely out of order. Yeah? I'll make that in a few minutes. So he says, why would you ever want to discretize your action space? But there's a good reason for it. Stay tuned. First, let me just convince you that, and sort of maybe to the spirit of the previous question too, one of the things I like about diffusion is that for the simple cases, like LQR, it does the right thing. For instance, if you were to if you had a linear dynamical system, let's just say, this is not expressing the power of diffusion. This is just saying, in the trivial case, it does the right thing. Okay, so you don't need diffusion to do LQR, but it'll do the right thing if you do choose to do diffusion, which is I find it super useful to do sanity checks like this. You can find bugs in complicated systems if you just ask what do they do on a linear system, for instance, right? So let's just take our known linear dynamical system. It can be stochastic, okay? Let's give demonstrations. It doesn't even have to be an LQR policy. That's sort of irrelevant, but let's just say it's a linear policy. So let's call this my demonstrator. Instead of human, I'll just put the system in initial conditions and let it run LQR for a while. Okay, the training loss, which would be minimizing the expected value over all the stochastic stuff of our denoising loss, which is going to look like a negative kx plus sigma conditioned on x minus sigma. Something like this. This is my expected value. It's going to be the sum over all the random samples I took. Okay. I'm going to minimize that loss. And the optimal denoiser, I don't actually need a deep network to do this. I could parameterize, it turns out to be a kind of a rational function, but I could parameterize a very simple function and do gradient descent on that simple function, and I could recover the LQR controller. So the denoiser that kind of like unwinds this and gives you the right answer with zero loss would be the one that looks like U sigma x. All it needs to do is learn this function, U plus kx. Okay, so like given those inputs, the denoiser should learn this. This is a vector pointing me back in the space to the answer U equals negative kx. And if you do the standard denoising, DDIM denoiser, it will actually recover U equals negative kx. Yes?
Prove optimality in like a more complicated case?
Prove optimality of which step?
I guess like you're saying here that LQR just pops right back out.
Yep.
For a more complicated case, would like the optimal controller pop back out without doing like HTTP or something?
I mean, I'm training this thing based on, so one of the things that's important to mention here is that there's actually, I've never said anything about a cost function, right? And that's actually one of the great things about imitation learning, potentially also a limitation, but writing cost functions, if your robot is trying to make a pizza, is hard. You don't know like even how to write the scoring function. Right? If I have to estimate the state of the pizza to write a scoring function, then I've kind of missed the purpose, right? So this is really, the only objective here is this MSE minimizer, just trying to minimize the squared error. And by this token, it is optimal because it achieves zero loss, which is the lowest possible. So this is like the optimal denoiser. But I don't think there's really any notion of the controller being optimal anywhere in the setup. A good question. Okay, yeah, and you can confirm in a few steps, but I won't write them, I guess, but that this thing, if you pop that in, is exactly the denoiser you would need when you run the standard scheduler. It'll pop out U equals negative kx. Okay, so I like that. You can stick a transformer everything, put a discrete action space or whatever, and it doesn't do this. Like somehow it's nice that in the simple case, this does the right thing. Okay, so that's one point. There's another point that I want to make, which I think is really simple but interesting, which is that I think both in the Aloha style behavior cloning and the diffusion style behavior cloning, they decided that they noticed empirically that it's very important to predict sequences of actions, not to just predict one action and then move on to the next step, but to actually predict a future trajectory of action, just like we learned about in MPC, okay? But it seems that the learning of the first action is fundamentally different if you ask it to learn the entire sequence. And if I just take this model and say like, okay, if I just had to predict a one-step cost, then the learning system only has to learn this kind of kx. Right? It didn't have to learn very much. But if it does have to predict some future action conditioned on my current state, then what does it have to predict? It has to predict something, well, it has to exactly this, right? Whatever it goes into the pipeline and comes out the other side, in order to get zero loss, it has to predict the future action. Okay, which in linear systems, it's almost too simple to be interesting. But when I look at this, I think, oh, that's pretty cool. So it actually has to learn something about the dynamics in order to drive the MSE to zero. Okay, but it doesn't have to learn the entire dynamics. This is, in my mind, this is the task relevant dynamics. by projecting it by k, so let me just, so in, like I say, the linear systems is almost too simple, but imagine I had a really big state space, and my optimal controller only used made decisions based on a few of the state variables. So k is very sparse. Right? The only ones I actually have to predict are the ones that were needed, the parts of the state that were needed for me to make my control decision. So it's I think that's a really interesting thing, is that when you're predicting future actions of a controller that was made its actions based on state, you had to learn something about the dynamics. Without ever explicitly estimating state, this could be like done in some latent place in the middle of the network, but it has to understand something about how things are going to evolve in order to make actions about, prediction about what the action will be in the future. And that's not a diffusion thing, that's just a behavior cloning thing, right? Okay, so I have a little highlight reel. Maybe you've seen it, maybe you haven't, but these things just really work well. So the egg beater was one of our favorite tasks because it's got a bimanual sort of kinematic constraint. If you didn't do this right, it would be very hard for the policy to sort of reliably turn the knob. It works with there's eggs in there too, okay? It does things that you would associate with the discrete kind of mixed integer kind of stuff that we've been talking about, right? So this is a very simple example of it. There's a bunch of examples of it, but this was trained both to unroll the mat to the right or to unroll the rat to the left. When it does it one way, it starts with its right hand. When it does it the other way, it starts with its other hand. Okay, and one controller looks at the state of the mat and figures out which way it's going to go, right? So this one now is going to do it from the other side. That's just a very simple example of it, but it does have this sort of discrete logic ability. This is another version of that. So this one was trained to like a particular page of the book, and it'll just flip pages depending on if it recognizes that page as too far in the book, it'll flip one way. If it was too early in the book, it'll flip the other way. Right? And surprisingly long horizon. We were thinking of this initially as only solving for like small skills, but you can train one diffusion policy, if you will, to like load many dishes. It'll just surprisingly long horizon tasks you can jam into one big network. Every once in a while, you'll train on a potato and be able to peel a sweet potato, or you'll train on a cucumber and you'll be able to train a carrot. But this is like, in my mind, outside the convex hull, and we just got lucky. Like this is not something I would guarantee in any case.
Would it a different shape of a cucumber be a farther problem than like a carrot and a cucumber being of similar shape?
So we bought a pile of cucumbers and we peeled like 200 of them or something, right? So I think it's got fairly good robustness to the shape of the cucumber. The thing we didn't do anything of is we didn't show it any carrot in the training data. So the question is just like, how far does it go outside the training data, right? I hear your point, but it just happens because of the angular way we trained the thing, yeah? Yeah.
Given the amount of demonstrations we do you think it would perform similarly if you just did like
So we did a lot of that kind of thinking at the beginning and convinced ourselves not. But I mean, it's possible we could, there's so many things about the infrastructure that got cleaned up that we could try that again. You could try that again, yeah, and see how well it does. I think it's doing more than just nearest neighbor. Yeah, it's showing, I mean, 200 demonstrations in this massive high dimensional space is not a lot, really. And it seems to be doing pretty beautiful interpolation, right? Oh yeah, I always try to pick something that nobody's seen. So this was just one from the other day. So pretty subtle one. You got to take the Ziploc bag, open it up. The Ziploc bag is basically invisible to a depth camera, so that's kind of a bonus. And that'll shake it out. Multi-step, long horizon. I'd say, I don't know, half the time the banana gets stuck in the hand or something like that, but So it's not, I'm not trying to say that these things work 99.9%. It is not close to that, but it can do a lot of things at like 50 to 80%, really impressively. Putting a towel on the rack and then putting clothespins on. So at TRI we have people that are training this all the time now, and we're getting more and more skills. Basically, almost anything you can teleop, you can play back. Yeah.
In a lot of these videos, the movement of the arm seems a bit
Jerky.
jerky.
Yep.
Is that a byproduct of it being a bit hard to teleop these things without being jerky? Or?
I think even if the teleop was perfectly smooth, we have some inefficiencies in our pipeline when we are evaluating our big models that we kind of know how to get rid of and we're working on now, but it was never a priority. You'll see people that, so there's lots of cool videos coming out all the time now. It's kind of become, the behavior cloning works well enough that I think it's kind of table stakes now for if you have a humanoid robot company and a dexterous hand, you're going to do a demo that looks like something's putting something in a dishwasher or whatever. And these are smooth motions. The ones we know about, a lot of them are using diffusion policy and they're doing it very smooth. So it's not, it's just the engineering work to get the kinks, the speed up of the big models. Okay, so I had a slide that I was trying to speak to. Oh yeah, okay. So why would you want to do discrete actions, right? I think there's like two fundamental problems about behavior cloning that people know about. One of them is dealing with multimodal demonstrations. The other one is about dealing with distribution shift. So let me say a little bit about both of those, okay? So multimodal demonstrations. I think the T-pushing has a nice symmetry in it that kind of shows that. But if you find yourself with an initial condition of your finger over here and you need to push the T this way, then maybe a human 50% of the time goes this way, 50% of the time goes that way, okay? And if you're not careful, then your neural network's going to go right up the middle, right? And like if you take just a multi-layer perceptron as your output and predict actions from that, that's what used to happen. And this, I think, was one of the big reasons why you needed an expert to do the demonstrations. The expert, one of the things that they would think about in their head was don't ever do different things from the same state. Try to be very unimodal in my demonstrations, okay? And the good demonstrators could do that, but the novice could not, right? In the discrete world, multimodality was not a problem, right? So just to say it right, so if I were, imagine thinking about like AlphaGo, for instance, was doing behavior cloning, and given an image of the board, you had to make a discrete action about where you're going to place the stone. And there was no sense of trying to filter the demonstrations for that. They took all kinds of expert players, right? People could have done different things from the same board position. And that wasn't a problem for AlphaGo back in 2016. So it's never been a problem sort of for discrete actions. I don't know, if I had a grid world, you know, my trash can robot that can move left, right, up and down kind of thing. And I had some sort of obstacle maybe here, and I've got an image coming in. My robot's here, it's trying to get to some goal here. Maybe 50% of the time it goes this way, 50% of the time it goes this way. But if my neural network output is, you know, the probability of taking up, the probability of taking down, the probability of left, the probability of right, then multimodal demonstrations are totally fine. You'll just get a, you know, maybe if it was half, you get a 0.5 over here, a 0.5 over here, and then when you're executing, you're just sampling from that probability and you're going to pick left or right. So categorical distributions did not have a problem with multimodal demonstrations. Go worked great, okay? But robots weren't working great because we required human demonstrators. And I think roughly what diffusion is doing is giving us the ability to represent the multimodality, or the multimodal nature, in continuous spaces. It's doing extra work, slower inference, in order to learn a distribution over possible actions, the log of the gradient of the distribution. Okay, so yeah, it worked fine for Go, but diffusion helped for continuous trajectories. That is somehow separate. In my mind, the diffusion output is like the decoder. So in the neural network parlance of we're going to take your images in, you're going to encode them into some latent vector, and then we're going to decode them into some actions. Okay, the denoising diffusion is a choice about how you're going to do the decoder. The encoder can be a full-on transformer. You can take language input. You can take image input. All the multimodal representations that we've been learning from language models, from visual language models and the like, those can be your inputs. And this is just a choice of, do you want to do discretized actions, do you want to do an MLP action, or do you want to do a diffusion action on the output? The other problem, the classic problem, you're going to be, why is that? This is the image that I always think of when I think about the distribution shift problem in images, or in imitation learning. It came from Drew Bagnell, who was talking about it back in the day, and Ross. So back in 2010, I think they were the most articulate in expressing the fundamental problem in imitation learning of distribution shift. And the example they gave was they had people train this racing game, Super Tux kart, okay? And you get a lot of demonstrations of people driving in the middle of the track, right? And then you have a neural network that's learning it, and the neural network gets it almost exactly right everywhere, okay? But there's a little bit of error, okay? And then, so your neural network, when you start to play it out, starts to get a little bit of error, and then it gets off a little bit to the side of the track. And you don't have much data on the side of the track, so you get a little bit more error. And then you don't have much data, you really don't have a lot of data there, and suddenly you fall through the sky, right? So this is the problem of distribution shift, because you're closing a policy, you're closing your policy, and if your closed loop dynamics takes you away from your data, then you've got a problem. And their proposed solution was famous. It was called Dagger. And they basically, there's a couple different ways to say it. Data set aggregation, it was their name for it. But roughly the intuition is take your first batch of data with the human driving however they did. But before you let the neural network drive all by itself, collect some other data where the human and the robot are basically sharing the steering wheel. Okay, and then you get data that is kind of on the fringe. The neural network's taking you off course, but the human's showing you how to recover. Okay, and in a loop of sort of aggregating that data, you can learn to be a robust controller and not walk away from the data. That's the original solution to that. In general, so at TRI, we don't do that explicitly. We do that implicitly, maybe, but we do tell our demonstrations, anybody who's demonstrating, if you came over and wanted to demonstrate, we'd say, if you screw up, keep going. In fact, that's the best data. And if you were to do like 25 demonstrations of getting it perfect, we'd be like, could you start screwing up, please? Because we want to see the recovery behaviors almost more than we want to see the nominal behaviors, right? And if we do collect a bunch of data and train for 3 hours on the GPU and then come back and we see it fail in a new way, then we might collect a little bit more data of how to recover from that type of failure, throw it back in, and do one more training run before we call it good. It's really interesting. So Max Semchowitz in our group has been thinking about the tension between those two problems, which is, it's kind of subtle, but I think this picture tells it nicely, right? So on the one hand, you want to support multimodality. On the other hand, you want to be stable, okay? So you don't have distribution shift. And it kind of seems like those things should be fighting, right? Going left or right around the obstacle feels like an unstable thing, but you also want to be stable so you don't walk away from your data. And so Max and team worked out about a way to think about the generalization that could make diffusion do this correctly. And what you want is a generalization you want the distributions to generalize in a total variational sense. Okay, so I need both my hands to make this work. Okay, so imagine I'm over here and I'm going left of the obstacle, and my probability mass is like completely over here, and there's no probability mass over here. As I move this way, there's kind of different ways I could ask. At some point I want my probability mass to be all over here and none over here. And the question is, how do you interpolate between those? How does the denoising diffusion interpolate between those? Okay, if it does it in the Wasserstein sense of moving the distribution from left to right, like Earth mover's sense, then you're kind of in trouble. You're going to go right up the middle, and you don't want that. Okay, if you do it in a total variational sense, where you kind of move probability mass, over like this, sort of, this one goes down, this one goes up, then you can break the tension between stability and multimodality. And some neural networks seem to do that in total variation. Some seem to do it in Wasserstein, and we're trying to figure out how the heck to make to control that. So people have done things on dexterous hands now. I think a lot of the humanoids companies are doing these kind of demos now. It's incredible how fast it worked. I would say one of the lessons here, Chung did many things right, but he made a repository that everybody can download and run, and that made a huge difference. Like, everybody just runs this thing. The other example you've probably seen online is this Aloha. They definitely got it right. They have these low-cost manipulators. They're a YouTube sensation. And I think somehow those pair of results seem to have been kind of the watershed. I mean, people knew behavior cloning kind of worked, but somehow I think it happened at the time where everybody's excited about language models, and now suddenly it feels like language models could go all the way down into dexterous manipulation. And that becomes very exciting. This was on my bucket list too, tying shoelaces. We did a version of this a couple years ago, but never on hardware because our fingers were too big.
That wasn't hard-coded, that was done with Diffusion?
This was done with Aloha, which is the other architecture, but that was a rollout of a demonstrated, that was not the teleop, that was the rollout, the autonomy. There's a particular way that you have to tie shoelaces if you're a robot. I don't know if you caught it. It's the same way we did it a couple years ago in simulation. And someone figured it out. We found it online somewhere, okay? But watch how it does it. There's like exactly one way where you can kind of loop your finger, and pull, and it just works, even though you got a 2-finger gripper. Watch this. Like that, like that, like that. Boom, that's the trick. No human ties it that way, but that's the way to make a robot tie it. And then the mobile Aloha somehow just really captured people's imagination. A lot of these were actually this one's autonomous, but yeah, they were cooking shrimp and all these things. And I don't know, somehow the combination of these things just got people super excited, and now it's amazing to see what happens. Okay, so I do think this is real, even in the more powerful architectures. I think you kind of, like in the original Aloha paper, they had a strip of tape which kind of indicated the range of initial conditions. In our setting, we know that if you go too far from the initial condition, from the demonstrations, things will fail. And that leads me to the second. So I motivated all that imitation learning work based on the, enabling control from cameras, right? So visual motor policies was one motivation. One thing that I think, it's not that you can do it with RL, you can do it other ways too, but I would say behavior cloning kind of unlocked some of the really rich representations in behavior cloning, because the training is so simple that we got to think about the architecture and make a lot of progress, okay? And similarly, the other thing that I would say is really going well is this move towards multitask. policies, which you could call our path to foundation models. So multitask has always been a thing in machine learning. It was a thing in multitask RL. It was very popular. But I would say this year we've seen more progress towards what we would consider to be these really serious multitask, where we have not only our observations going into our dynamic policy, but also, for instance, our goal being parameterized by, for instance, language conditioned policies. And somehow the thing inside here is something that knows how to answer basic, natural language questions. Okay, so we're getting to the point where you kind of can just say, "Robot, make me a pizza," And it might not be a very good pizza, but it has like a reasonable chance of doing sensible things if you feed in enough data and go through this pipeline. And for me, that fundamentally challenges some of the questions about control, right? So, there's a couple things that happen with it, but we didn't think about that very often in control. Let's just think about the implications of that, right? So, if I do many different tasks, okay, I put my robot in front of the pizza, I put my robot in front of a shoe, I put my robot in front of the laundry that needs to be put on the hanger, okay? If I were to take everything we've talked about to class, what I would do, I would start by making a simulator, let's say, okay? I'd have a state space representation of the task. Let's say my X has 20 variables, okay, for the pizza. That would be really impressive, but let's just say I have 20 variables for the pizza. I might have 25 variables for the laundry, and I might have the different number for the shoes, whatever. So how do you write a single controller that not only does different tasks, but is fundamentally working on different dynamical systems? The state is different in all those tasks. Okay, philosophically, maybe there's like a state of the entire universe that is common across there, but that's not the states we've been using for our control design. So that challenges me, because so we talked about belief space planning as kind of the heavy-handed, but the sledgehammer, that if you could always choose the belief state to be your representation of state. That would always be sufficient. But even the notion of belief state requires you to know what X is. It's the probability distribution over X. We don't have that here, right? If I have one robot, one policy that can be told to make a pizza or fold the laundry or whatever, then I've got something I haven't quite got the language so far in underactuated to talk about. And that's awesome. That's a challenge. That's because there's every reason we could talk about that. So the challenge for you, for us, is to, so what is the right way to think about that? Like what is the right, maybe simple way to parameterize distributions of tasks, of plants, that would be amenable to the clear thinking that you can do in control, okay, but gives us insight into what must be happening inside these bigger models? What does learning a representation that works for those many tasks mean? What is it optimal? I feel like we've opened up new vistas, but the success is undeniable, but we're on a bit shaky foundations. I don't really understand what's going on in a lot of these things the way I understand other things, right? And that's a great place to be. But we have to, I think, be very careful to articulate some of these new challenges and study them. I think LQR is not rich enough for that one. I think we need a little bit more than LQR. But what is the minimal thing? Is it a compass gate? Is it really it's probably not a compass gate? But it's there's going to be a simple incarnation that permits clear thinking for these new problems. And every one of these new problems. I could make a longer list. This one stands out for me. So I think we're seeing this transition of people thinking about, LLMs, and then we had visually conditioned language models, and now we're having foundation models for manipulation. TRI calls them large behavior models. Some people call them VLA, vision language action models. Some people call them embodied foundation models, robot foundation models. The list goes on, but these are coming, and we don't really know how to think about them yet.
Can you talk about your thoughts on how these kind of policy generation mechanisms translate to safety critical systems like autonomous cars and aircraft?
Yes, I can talk about that. So I probably wouldn't put this immediately on a safety critical system, but if you would, I think there's still a role where a common thing in learning safe learning autonomy would be to put like an envelope controller around you. And that's kind of what we're doing already in the TRI case. So we have a low-level controller that knows where the table is. It won't let either the teleoperator or the policy slam the robot into itself or into the table. So there's kind of a safety case already built around that. It can't guarantee anything about the pizza, but it can guarantee things about the things it knows. And that's enough to make a lot of the safety case checks we want. And I would say the same thing about, so if the safety of your autonomous driving depends on your inference about the pedestrians, then that's hard. But if it's about speed and, so the things that are that our current less learning approaches can guarantee, then those safety cases can be built up. Yeah. I remember years ago talking to people like in defense contractors, asking them about deep learning perception. How could you make a safety case around this if you're gonna? And I remember being moved by the idea, someone said to me, if it works better and the job gets done better, then we can't not use it. We can't not use the technology if it actually just accomplishes the job that much better. So we will have to evolve our notion of what a safety case means. But if it just accomplishes these tasks that we couldn't do, we should be open to that. But I will say, yeah, please.
Sounds like something in a defense contract.
An unnamed defense contractor. But I do think what's happening here is we're making generalist robots that will be kind of good at a lot of things. And that is not what you want for a product out of the box. But then when you take that capability and you try to go vertical, you can bring this generalist capability in. And I think when you do try to go for 99.9% on something, if you can bring with you the ability to make pizzas, but also like recover when all kinds of crazy corner cases happen, then there's a kind of a common sense robustness that you could potentially have in the vertical direction that we've never had before. So I'm willing to be a little sloppy, but diverse for a while because I want that sort of common sense of like, okay, one of my fingers fell off, but I can do something still with the rest of my hand or something like this. That kind of robustness that you only get by trying to do everything. Yeah?
What kind of architectures are the dynamic policies?
Yeah. On the single task cases, it was like ResNet encoders to the standard UNet sort of diffusion output. As you get to more visually rich, the ResNet encoders slowly made way for the VIT kind of encoders. And then when you start using backbones that know how to talk about language or are pre-trained like a visual language model, they get bigger and bigger. But you can take the encoder side of things and make it, I think they're going to probably look more and more like a VLM as an input. Pre-trained on VLM type things, possibly with some robot-specific VLM type things. Yeah. Yes? Oh, I thought you were saying you're going to clone the engineer.
Well,
like you were going meta on me, yeah?
No, in a way. I mean, I guess it's basically like you show it a bunch of examples of given this sort of abstract thing, how do you formulate that into a problem, and then you're like refine your controller, and you get a stable controller for the particular action.
Yeah.
And then now that you've given it sort of that ability to hone in, maybe generally it doesn't do it
Good, 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 good. So, okay, so when everybody started playing with GPT, I feel like you had to kind of go through this learning curve, right? The first time you go to GPT, you sort of say, I'm going to ask it anything, it's going to give me the right answer. And then you're like, okay, it doesn't always give me the right answer, so this is a pile of junk or whatever. And then you're like, okay, actually, if I learn how to use it, it doesn't always give me the right answer, but it's super useful. And I think there's a kind of like there's ways to interleave humans and autonomy that has this kind of like, I can almost do lots of things in ways that we have to reimagine the way to work with these, but I think they're going to be super useful. That sort of Dunning-Kruger GPT thing is going to be here too. Yeah. Okay, let me wrap it up. So everything we learned, I think, puts us into a position. I hope that you saw a little bit of the window of sort of, I think, clarity that we can potentially have for very complex problems. I do think this stuff is changing. What's happening in the world, we should embrace it. There's some cases where you don't need this. This is like when you need to be multitask, when you need to be visual motor, those are the things that I think really motivates this. If there's certain, military applications or anything that could be better off with model-based tools. But in this space, I still think that learning the things you've learned, the career I've spent or whatever, it's still valuable, right? And we should aspire to bringing some of that clarity, because it's not we've been able to think clearly about very complex things, and we can think clearly about this too. But it demands a level of rigor and maturity that we have to bring to these new problems. And you have to be open-minded about what's changing, but stubborn about believing that you can understand, right? So do that. Cool, okay. See you Tuesday, and it's your turn.